Alright, welcome to Math 1910. We're going to be doing a little algebra review here. So we're going to step into Chapter P, go into Section 1. We're going to take a look at graphs and their models. Alright, so just basic review, because if you're going to struggle with calculus, it's not the calculus concepts, it's with the algebra concepts. So I want to make sure that we have time to review through the algebra concepts and solidify them before we step into the calculus concepts. Okay, so a lot of this is going to be reviewed, but it's stuff that you may not have done for a year or two, or stuff back from maybe Algebra 1, parts of Algebra 2, and we need to make sure that we bring all those fundamentals back. So we're going to sketch a graph of an equation, find the intercepts of a graph, we're going to look for symmetry, we're going to find where graphs intersect, and we're going to interpret some models of real-life data. Okay, so if we take the analytical approach here, all right, if we understand the graph of equation, okay, so we're given an equation in standard form, 3x plus y equals 7. All right, and we are given that the point 21 is a solution point of the equation, because what it means is anytime I plug in 2 for x and I substitute 1 in for y, I do in fact get 7, right? If I substitute in 2 times 3 is 6 plus 1 in for y, which is 7. So we can see that it satisfies the equation. And remember, this is a line, so there are many other solutions to this because it's linear and it goes on forever. Now, what you need to remember is, all right, it's given to us in standard form, right? Ax plus bx equals c. So for us here, all right, it's always common for us to solve that equation for y so that it's in slope-intercept form. So when we say that y equals 7 minus 3x, okay, that's the same equation above, solved into slope-intercept form. We understand that the slope of this equation is -3 and the y-intercept is 7, so that we can get some other valuable information of it. You can also make a table of values. I believe most of you guys know how to do that, right? We substitute values in for x and we get our y value out once we're in slope-intercept form. Makes it a lot easier. We can also put it into our calculator, into y equals, and take a look at the table that way. And so we're able to graph this, based on getting values out of the table that we created and putting those points on a Cartesian coordinate graph and then drawing a line through them. So we can see that this is the graph of 3x plus y equals 7, but it might have been easier for us to understand that it was y equals 7 minus 3x. We can see that it goes through the y-intercept at 0, 7, and that it's a graph that's decreasing because the slope is negative, and it's -3, which really means -3 over 1. So it's going to go what? Down 3 over 1, down 3 over 1. And that's a good way for us to indicate, how to calculate the slope. Now we can also substitute in, we can substitute in all the different values of the table and plot it much more accurately as well. All right, so let's take and sketch a graph. We should recognize this graph. This is a parabola. All right, how do we know it's a parabola? Because it's x squared. And what's happened to that x squared? It's been shifted down 2. So we should visually understand what this graph looks like, right? It's going to be a parabola shifted down 2. Now for us, okay, it might be easy for us to just, create a table of values. So plug in values for x. So plug in 0, plug in -1, plug in +1, plug in -2, plug in +2. And see what's really going on with that graph. Okay, so it should just be review for you guys. Okay, this shouldn't be anything new, but I just want you to understand. I need you to be able to look at this graph and be like, oh, that's a parabola shifted down 2, and it'll make sense. Eventually, we're going to calculate, the slope of this graph, and we're going to use calculus to do it. And then we might find the acceleration of a particle that takes this path as well. So once we get our table, right, we plot the points. And we can indeed see that this graph is a parabola. All right, it's x squared shifted down 2, and it has symmetry about the y-axis. I'm going to use that term early on here. All right, when it's symmetrical about the y-axis, which means if I were to cut it straight down the y-axis and I folded it in half, it would sit on top of itself. Okay, so we're talking symmetry about the y-axis there. Other important aspects of graphs that we need to calculate are called the intercepts. Okay. Those are where the graph crosses the x-axis. Sometimes it has no intercepts, and that's fine. Okay, other times it might have multiple intercepts. Those become very important later on when we are able to graph things using calculus. It's very important for us to find the intercept because we can take a look later on if a function is increasing or decreasing, if it's accelerating, decelerating, doing all those different kinds of things. So for us to be able to understand how to calculate the intercepts on a graph is very, very important in calculus. Okay, so sorry, I'm going to step back a slide here. When we calculate the x-intercept, remember the x-intercept is when y is equal to 0, and we solve for the values that cross the x-axis. If we want to find the y-intercept, it's when x is 0, okay, and where it's crossing over the y-axis. Now when we're in a slope-intercept form, that's easy, right, because we're given y equals mx plus b, where m is the slope and b is the y-intercept. So that's where the point 0b is showing up here on the slide. Okay, that's from that's finding the y-intercept using slope-intercept form. Okay, so, and like I said, I'm hustling through this because it's algebra review, but if you have questions, ask me, but we do need to make sure that we have the basics here. So let's look at each one of these graphs here. The graph on the far left, all right, the parabola. Okay, look, there's no x-intercepts, right, because the graph has been raised up. But there is one y-intercept where it crosses the y-axis. Okay, very important there to understand that one. If we look at the second graph, that's a cubic function. Okay, it has 3 x-intercepts. Generally, as long as the graph has not been shifted, that tells us, how the power tells us how many roots there are. Okay, intercepts are roots in general. Okay, so if it's a cubic function, there should be 3 roots. If it's a parabola, there should be 2 roots. However, those roots are not always real. Remember, we can use imaginary numbers and things like that. Okay, now look at the third equation. Okay, that third equation is x equals like y squared, or y equals plus or minus the square root of x. Okay, we can see that it has 2 y-intercepts here, and that it has 1 x-intercept. And then the last graph, we can see that it's a circle. All right, and then in this case, there's no intercepts, there's no x, there's no y, but it does still have a radius, so that is important to make sure that we understand that. Okay, so as we get into it, we want to find all the x and y intercepts of this function. Okay, so let's take a look. We have the function y equals x cubed minus 4x. So in my mind, I'm knowing that this is a cubic, right? The power is 3. I should probably have 3 roots. Most likely real, but not necessarily. We won't necessarily be harnessing in on imaginary roots yet here, but just so you know, you should have 3 roots for this polynomial here. Now, the best bet, we have x cubed minus 4x. Well, there's no other constant term at the end. So when I see like an x cubed and an x term, the first thing I'm thinking in my head, I need to factor out an x. Okay? So remember, that's what we're going to do, but I want to reiterate. Well, we want to find the x and y intercepts. So the y-intercept's pretty easy for this one, right? When we set x equal to 0. So if we substitute x equal to 0, both of these, y becomes 0. The tricky one is finding the x-intercepts. That's when you set those equal to 0. So we're going to factor those out and find them. Okay? So if we take a look at this, the x-intercepts, we're going to let y equals 0 and solve for x. So we're going to say 0 equals x cubed minus 4x. Okay? Then we're going to factor out an x. And when we factor out an x, we're left with x squared minus 4. You have to remember that x squared minus 4 is the difference of 2 squares. So x squared minus 4 factors into x minus 2 times x plus 2. So when we factor that entire equation, factor an x out first, and you're left with x times x squared minus 4. And then factor x squared minus 4 into x minus 2 times x plus 2. So that's where those come from. Now we set each individual component equal to 0. So you're going to set x equal to 0, you're going to set x minus 2 equal to 0, and you're going to set x plus 2 equal to 0, and solve for x in each scenario. So those will give us our 3 roots. So x equals 0 is one of them. Then when we solve x minus 2 equals 0, we get x equals 2 as a root. And then when we set x plus 2 equal to 0 and solve for x, we get negative 2 as a root. So our x-intercepts are 0, 2, and negative 2. All right, easy ones. Now, the y-intercept, Okay, when we go through that, we're setting, I'm going to step back a slide there. The y-intercept is at 0, 0. Remember, that's when we make x equals 0. And I talked about that at the beginning. So if we go back here and we look at the original function, when x is 0, we get 0 cubed minus 4 times 0, so y equals 0. So there's where our y-intercept comes into play there. Okay? And then we're able to kind of graph this function. You'll be able to graph this function, without a calculator later on using calculus, because there's different rules for the first derivative and the second derivative that are going to help you determine whether the graph is increasing or decreasing on certain intervals. So that's going to be very important. But if we graph this function in your calculator, okay, this is x cubed minus 4x. So if you graph this in your calculator and you hit zoom, 6, you would see this graph, and you could change the window so that x is -4 to +4 and y is -4 to +4. Your window would look exactly like this. But the roots that we just found are what? -2, 0, 0, 0, and 2, 0. So they share a root, right? The y-intercept and an x-intercept at 0, 0 is the same. Okay, so there's plotting all the roots. Those are going to be very, very important for us in calculus. You're going to make sure that you have to remember these rules to factor, set each component equal to 0, and solve for x when you're finding the roots or the intercepts for x, okay, and how to find the y-intercept. Okay, so it's very, very important if we know the symmetry of a graph as well before we start graphing it and sketching it. Okay, so there's 3 different types of symmetry that we can take a look at. Okay, symmetry about the y-axis, right? So I've talked about this before. If something is symmetrical about the y-axis, if we cut it down the middle where the y-axis is and we fold it over the y-axis, it will fold on top of itself. So we always determine that as being symmetrical about the y-axis. We can also verify it with points. So if I take the point xy, and you can see that on the graph here, and then I take the point -xy, so I take the opposite of x, and I keep the same y value, this function will be symmetrical to the y-axis. Okay, so there's going to be questions on your homework that ask you, is it symmetrical to the y-axis, the x-axis, or the origin? And based on this rule right here, if you write this down, you'll be able to see that. Because you might not have a function, you might just have some points or things like that that you have to determine that from. Okay, so we can see that the y value remains constant, the x value is the opposite of itself, so therefore we can conclude that we're symmetrical to the y-axis. Alright, with symmetry to the x-axis, same kind of concept, only now it's, relative to the x-axis. So if we were to split the graph where the x-axis is and fold it on top of itself, alright, it would be able to sit on top of itself, so we know that it's symmetrical. It would mirror onto itself across the x-axis. So in this case, the x value remains the same. The y value becomes the opposite. So that's how we can determine if there's symmetry with respect to the x-axis. Folding it over the x-axis and it lays on top of itself, it's symmetrical to the x-axis. Lastly, if we have symmetry to the origin, which means you have to fold the graph twice. If you fold it over the y-axis and then if you fold it over the x-axis, or you could fold it over the x-axis and then over the y-axis, if it lays on top of itself, it will have symmetry to the origin. So how do we know this graphically? If we take the point xy and we're able to graph the point -x, -y, so we're taking, or -y, so we're taking the opposite of x and the opposite y, and we're able to graph this, this means the graph is unchanged by a rotation of 180 degrees about the origin, which means it's symmetric to the origin. So you can also, visually in your head, if you can rotate this graph 180 degrees around the origin, it will also have symmetry to the origin. Okay? So here's the test for symmetry that you're going to do. So I would make sure that you have this in your notes. Okay, I'm just going to kind of read these off, but this is really how you're going to do it. All right, the graph of an equation in x and y is symmetrical with respect to the y-axis when replacing x by -x yields an equivalent equation. Okay, we're going to do examples by this. So if I take an equation and I substitute in x, all right, and I substitute in a -x and I get the same equation back when I substitute in a -x. Most likely, right, that's going to happen when I got a parabola or something like that. I'll get the same equation back. That means it's symmetrical to the y-axis. Okay? Then, the rule for testing for symmetry to the x-axis, okay, if I replace y with a negative y and I get the same equation back, I have symmetry with respect to the x-axis. So what you're going to have to do on your homework problems here is you're going to have to do this test for symmetry for each axis and see. So the third one is the graph of the equation to see if it's symmetric about the origin. That means you have to substitute in a negative x and a negative y into the original equation, solve it. If you get the same equation back, you have respect to the origin. Okay, so you will have homework problems on this. So we can test this graph here. All right, we can see that if I substitute in negative x for x here, right, I literally replace it. So I'll have negative x to the fourth. Negative x to the fourth, since it's an even power, gives me back an x here, and then I take negative x squared. Negative x squared will give me back the same x. So if I substitute in a negative x value here, all right, I will get back the exact same equation. So I know it's symmetric to the y-axis. Now, since I know that it doesn't give me the opposite x backs, I know that I'm not going to get the origin piece. But just to check, right, if I substitute in a negative y here, if I put in negative y, I do not get the same equation back. So it is not symmetrical to the x-axis, therefore it's not going to be symmetrical to the origin either. So this is only symmetrical to the y-axis. Alright, so let's take a look at this. We want to test for symmetry with respect to the y-axis and the origin of this function here. So we have y equals 2x cubed minus x. So for us to test symmetry to the y-axis, we're going to substitute in a negative x in for the x's. Okay? So let's take a look and see what happens when we do that. When we substitute in a negative x here, all right, we have negative x cubed. That produces a negative x cubed. Okay? So when we substitute in a negative x in for both x's, we get a different equation. We get a negative x cubed plus x. So we know it's not symmetrical to the y-axis because we did not get back the same equation. It's not symmetrical to the y-axis. Okay? Does that make sense? How we substitute in an x, a negative x, and if we would have gotten the same equation back, so if we would have gotten 2x cubed minus x back, all right, we would have concluded it's symmetrical to the y-axis. So in general, if you have even powers, it's most likely going to be symmetrical to the y-axis. If you have odd powers, it's most likely going to be, symmetrical either to the x-axis or to the origin. So let's check the origin now. So remember the rule for the origin, we have to plug in a negative x and a negative y. So we're going to take this equation here, y equals negative 2x cubed plus x, because we already substituted in the negative x, so we don't need to do that again. I need to substitute in a negative y and see if I get back the original equation of y equals 2x cubed minus x. Okay, so we already did the first part by substituting in the negative x. I'm going to show it again here on the slide, but you don't need to do that. But if we substitute in a negative x and a negative y into this equation, okay, if we divide by negative 1, right, we got to get y by itself, so we're going to divide the entire equation by a negative 1, we end up getting the same equation back. We get back 2x cubed minus x. So for us in this scenario, it is, all right, symmetrical about the origin because we plugged in a negative x and we plugged in a negative y and we got the original equation back. Okay, so you had to do that at the same time, plugging in a negative x and a negative y at the same time and getting the original equation back. Therefore, we are symmetrical about the origin. Okay, and if you graph this, you can see it. If I take this graph and I fold it across the y-axis and then I fold it across the x-axis, I will have symmetry to the origin. Very, very important that you guys remember how to calculate symmetry about the x and the y and the origin when we do that. So make sure that you have those 3 rules down that we did on a previous slide. Okay, points of intersection. Okay, what does it mean to have points of intersection? That's where 2 graphs cross each other and intersect each other. Okay, very important for us to do that. That was called solving simultaneous equations. You might have used matrices. All right, there's different methods, for solving simultaneous equations and things like that. All right, so we want to find all the points of intersection of the graph of x squared minus y equals 3 and x minus y equals 1. Well, one thing for you to do is graph it in your calculator, right? But for you to graph it in your calculator, you're still going to have to do some handwork, right? Because you can't just plug x squared minus y equals 3 in your calculator. You have to put both of these equations into slope-intercept form. All right, so you're going to solve the top equation for y and the bottom equation for y equals. Okay, but this is really what we're looking for. We want to see, we have one that's a parabola, one that's a line, and we're looking for the points of intersection so we can sketch them on the same graph. Okay, so when we do that, we solve the first equation for y, the second equation for y. So we know that the first equation is x squared minus 3, parabola shifted down 3, and we have x minus y, a line shifted down 1. We want to know where they intersect. So the most common one for you that you learned, since they're both equal to y, I can set both of these equations equal to each other and solve for x. So I can set x squared minus 3 equal to x minus 1. I'm going to solve for x. Okay, I'm left with x squared minus x minus 2. So I want to factor that. That factors into x minus 2 times x plus 1. Remember, factoring in this case, if I'm looking at the general form here, x squared minus x minus 2, it's two numbers that multiply to negative 2 and add or combine to give me negative 1. So that's why we have x minus 2 times x plus 1. We set each one of those equal to 0 and solve, so we should see that it works when x equals 2 or when x equals negative 1. Those are the solutions there. Remember, that's the x piece. We have to substitute these back into the original equation to find the two y values. Okay, it doesn't matter which original equation you can use. You can use the first one or the second one, but you got to substitute x into that to get the y value back. Okay, so we're going to substitute x equals negative 1 and x equals 2 into the original equation, and when we get that, when we substitute in 2, we get back 1 for y, so our first point of intersection is 2, 1, and then when we substitute negative 1 in, we get a negative 2 back, so our second point of intersection is negative 1, negative 2. Okay? So lastly, we'll just talk about some mathematical models, all right? How we did a lot of this in pre-calc 2 and things like that, so that should help. All right, but we have data that we want to make sure that it can be represented in some sort of mathematical model and things like this. Okay, this talks about the Mauna Loa Observatory. So this is on the Big Island in Hawaii. Very cool. Been there. If you ever get to the Big Island, you should need to go there. It's sitting up on top of the active volcano. Very cool volcano. You can see around it, drive around the cauldron. You can see it fill up and go down and things like that. There's a seismograph there that measures earthquakes and different things like that. Okay, so it records the carbon dioxide concentration in the Earth's atmosphere around there, all right, because there's a volcano, it's giving off those toxins and things like that. So we can see, what I really want you to understand here is it's giving off the CO2 in parts per million from 0 to 1960. So we're taking a look at the years here. So the biggest focus that I want you to understand here, okay, is understanding how we equate the years down below. So it's really going from what, 0 to 60, okay, or 55, kind of how you see it on the graph. But that represents 0 to 1960, okay? So what we want to look is they're using this model here, y equals 0.018 t squared plus 0.70 t plus 316.2. All right, they're using that to model the data from 1960 to 1999. What you have to remember here is do not plug in 1960 or 1999. Those represent years, so time in years. That's 0 to 30. So the biggest mistake people try and do is plug in like 1999 or 1960 or 2000 into these, instead of actually plugging in, time. So 1960 is our base. That's when time is 0. So that's when t equals 0. If we wanted to calculate the value at 1990, we would have to calculate it when t equals 30. Okay, so time equals 30 years. Okay, so very, very important that you guys understand that. So we can use the linear model here. Y equals 1.68t plus 300.5 for the data for any time between 1980 and 2010. Okay, now that's also a span of 30 years as well. So you really got to be careful when we're substituting into this data, all right? And what t is when t is 0, still at 1960. Okay, so let's take a look here. We want to answer this question, all right, for the year 2035. 2035, you have to remember that when t is 0, it's still 1960. So from 1960 to 2035, that's 75 years. So that's why we're going to substitute in t equals 75 into the quadratic model here. So we get 469.95. The carbon dioxide concentration in the Earth's atmosphere would reach about 470 parts per million in the year 2035. Okay? We can kind of verify and see if their model's right because this model was made a while back. We're much closer to the year 2035 as well. Okay? So, the prediction for the year 2035, like if we used the linear model, okay, was 429.5. So if we look back, if we used the quadratic model, it was 469.95, and then we used the linear model for the same amount of time, it's 429.5. So it's actually less. So this is where you got to really, pay attention to who's predicting data and how, all right? There's going to be a lot of false numbers and things like that. You see it in a lot of the data that you see today, all right? It just depends on what model you're using. So if we used a quadratic model, probably not the best fit for that data, right? It was coming in very high. But if someone uses that model, they're going to maybe use it as their scientific data and say, no, it's holding true to this, all right? Versus the linear model, much lower, probably more realistic, all right? But people might ignore the linear model, even though the linear model might be more correct and accurate, all right? So if we take a look at it, okay, the 1990 prediction, all right, was too high for the linear model. So, it's just different things like this and being able to interpret data and using the right models and substituting in the right values and doing those sort of things. Okay, so guys, this has just been an algebra review. So basically we should understand how we're graphing functions, finding x-intercepts, y-intercepts. Okay, understanding symmetry, if we have symmetry about the x-axis, the y-axis, or the origin, and then being able to model data. Substituting in values to see if they make sense and that sort of thing. So I know that this is mostly a review, but it's algebra skills that we got to solidify before we step into calculus, because what bogs you down in calculus is not being strong enough in algebra. So we are going to rock through the algebra review in this course. Alright guys, if you have any questions, feel free to email me. Let me know if you got a team or Zoom meet or anything like that. Else guys, have a great day. I'll see you in class.